This is one of these chess timer talks. In case you haven't been in one of them before, the rules are pretty simple. The idea is basically that the speaker has 20 minutes of speaking time, and the audience has the other 20 minutes, which means you guys actually have to make some effort. Yep. Oh, okay. Sorry. Thank you. So you guys actually have to make some effort to participate in this. You can't just, let him time out at 20 minutes and then just walk out of the room. You guys should be raising your hand and asking questions. He's designed his talk to try and get you guys to, to him. So, I put the responsibility on you guys to raise your hand if there's something unclear at all, and then ask. The chess timer is a little bit weird. It's supposed to be 20 minutes for each speaker and audience, but this chess timer only operates 25 minutes. So subtract 5 from this, but I will raise these signs to let everybody know when they have 5 minutes for the audience or 5 minutes for him. So, sorry.
Okay. So my name is Jörgen, and I'm going to talk to you today about functional programming and foreign language interfaces, which are, I think, the essentials of distributed computing, but we'll see. Yeah. And a few words about myself. I'm currently on a PhD position at the Humboldt University in Berlin. I am the creator of the scalable workflow language Cuneiform, which I'm also going to talk about today. And the major field of application for this language is bioinformatics, but it turns out that the language can be used also in very general scientific applications, but we come to that. And yes, this language, Cuneiform, as I said, is a scalable workflow language, and it borrows from functional programming a lot and allows the reuse of existing software, which is quite important, I think, because people in the who are willing to do scientific data analysis don't want to first port their software or write wrappers for using them. But a little bit more about the problem domain. So what we're facing today in the field of bioinformatics, and especially in next generation sequencing, is that there's coming up a new kind of hardware which is capable of producing data extremely fast, extremely much, and also you can operate it very, very well in parallel. So it's natural to say that if we can generate this data in parallel, we also have to analyze it in parallel in order to keep up with the pace. Yeah, and what is also quite interesting is that the cost at which we produce this data is dropping even faster than Moore's law. So it's not only a halving of the costs every 18 months, but it's even better. Yeah. So the challenges are even more. So this graph reverses the view a little bit. Here we look at the throughput of these sequencers, which are the yellow and the red curve, and the blue curve is how fast the capacity of our hard disks is growing, and it looks a little bit. This is a little bit a misleading graph because you see this this point where the lines cross. This is not really the problem point. Is just where it's just yeah, the lines intersect there, but that has nothing to say. But what is important about this graph is that the cost or the throughput at which we get these machines to work grows much faster than our capacity to store this data. Yeah. So, and the next problem is that if we look at this scientific domain and all the people that work in there and all the universities that contribute software, it turns out that this is a very diverse field with many people and many sources of contributions. And this is a screenshot from a website, SecAnswers, which enumerates here only the categories of tools that are available in this field of research. And in parentheses, you also see the number of tools that are categorized in there. And this is a huge amount of software that is at our fingertips, and we also need to be able to use that. It's not if you come up with the next data analysis platform, you can't just say, okay, and everybody migrate their software to our platform. You have to have a way to incorporate what is already there, because these people won't sit down and rewrite their software just because you have a fancy tool. Yeah, and this is kind of the problem setting. To reiterate, we have a lot of software that we need to reuse. We can't just re-implement it, and also wrapping it is kind of costly. We have machines that generate data at a very great pace, and that it can be operated also in parallel. And this is kind of the what do we do now? Yeah, and this is a question I ask everybody. This is kind of the point where you can interact with me. So
Exactly on time. It was exactly 5
yeah,
minutes.
okay.
It was perfect.
Oh, this was 5 minutes. Okay.
Yeah. Now
And
you've only got another 15.
and to keep you to put you a little bit on the spot, um, I will ask this question to I ask this to myself, but this is a very important question I got from the users. Why would you use anything like general purpose? Why is a general purpose programming language not up to the task? Yeah. What is wrong with Python? Why can't you solve this with Python or Perl or whatever?
Efficiency at all, so that as you're passing things in and out of Python processes, you're trying to use that just as equivalent to scripting language.
Yeah.
Next time.
Sorry, I was just saying. So you asked the question of why wouldn't a general purpose programming language be sufficient? Is it partly about performance, because if you've got a lot of data flowing in and out of different processes and you're just trying to coordinate it
Mm.
with a scripting language,
I-
would that actually do?
Yeah, so the thing is, since you're using all the kinds of tools, I guess the tools that don't get faster just because you drive them from Python or from anything. So the tools are just as efficient as they are if you don't re-implement them or touch them in any way. So it turns out that exactly as you said, uh, there was this blog post or this paper from Austerhout in the 1998, where he said that scripting languages set out to be the gluing of applications. So you could say that for Python or for Perl or these scripting languages, it is exactly this is what they try to achieve, right? To to be the gluing code for all these foreign tools. But it turns out that there's other things that are complicated. And I personally think that of course it's possible to do in Python or in Perl or whatever scripting language you have, but the hassle is a little bit disturbing. So what you need to do is, first of all, you need to have a way to import all these tools in let's say Python. For command line tools, this is not so hard to do because you have this command OS, like you defer the control to the operating system and you get your answer back. But what if you have, for example, a code snippet in R? Then you have to first wrap your R code in command line, and then you have to call your command line tool from Python, and then it's not impossible, but perhaps we can do better. Yeah. So the cost of wrapping is something that you can reduce at that point, and also what most of these scripting languages give you is there's libraries where you can parallelize, for example, a map. Yeah, you don't have to do it like sequentially, but you can do it on multi-core and use all the capacity of your multi-core system. But what may be even harder is if you want to do it on multiple machines, right? Then there still may be libraries in Python or R or Perl that give you that, but it doesn't come out of the box. The user needs to know these libraries, he needs to drive these libraries, and he needs to know what to do. It doesn't come automatically. And this is where we can improve. And the second remark, perhaps that I'm curious to hear what you have to say about is bioinformatics is built on Unix tools, and the philosophy needs to make its way to the big data stack. So if I'm going to provide a tool that does big data, and I wanted to work in this bioinformatics environment, I just need to have a way to import all these Unix tools, and then I'm done. Is that so?
So there's a microphone, so we can.
Big data tends to happen in big corporations that they are very special about their IP. So sometimes I've seen internal tools that are built on top of the current open source ones, and those are never going to see the light of day because you know that lawyer team is probably more powerful than the rest of the company
Yeah.
put together. So I think that's one of the reasons why the field may feel a little bit underdeveloped because most of those like high-end tools are kept secret or indoors.
Yeah, that's true. I think so too.
I also have doubts about the first part of your claim. Is it really built on Unix tools?
Exactly. That's exactly what I think too. It's if you look at this plethora of tools, you can't expect them all to be command line tools. Some of them will be R libraries, some of them will be Python libraries, some of them will be have different APIs. Yeah, it is so easy to um, to end up with an arbitrary API, and you still need to drive that. Yeah. So the multi-language aspect is very important here.
Yeah, so I just have a thought about the first part where you're talking about the speed of hard disks or like the storage capacity is not as fast as the amount of data that you're getting.
Yeah.
And I mean, clear at some point, the storage is gonna be totally insufficient. There's no like you can't use compressor. So maybe the idea that's needed is another Unix concept, which is like pipes and streams, where you just have to look at the data as just a host of data that you can't look. You just have to dip in and look at the stream live, kind of that model.
Okay.
Like you have to have a shift of models instead of storing that and then looking at it.
Yeah, this is a valid approach. If you're allowed to throw away the data after you analyze it, you can get rid of the raw data quickly, but only keep the knowledge you get out of it. Uh, what I think is stands a little bit in the way of streaming is that oftentimes these tools get replaced, so the standards also change from time to time. This is not often, but from time to time, the standards of how should I analyze this data change, and then it would be extremely valuable to still have the raw data at hand and redo the computation because as you go, as the algorithms improve, also the knowledge that you could get out of this data that you might have been throwing away, uh, you still have that. So it's also a worthwhile activity to store the data, even if it's costly. And another approach you could have is like, as you said, streaming, not to build hard disks, but to build refrigerators where you keep all the samples, and sequence them as you need them. But that's a different kind of thing. It's not that worse yet. Yeah. So we're still getting bigger hard drives, and we still and it's still cheap to store stuff, but we might run into a problem soon. Yeah. So this is like, yeah, something that drives cost eventually. Okay. So here, this is again, command line tools wouldn't be sufficient in the end. We also need other languages to be supported. And when we look at how the scientific community approaches this problem, there's this keyword of scientific workflows. And a scientific workflow is essentially a description of an analysis task as a graph, as a directed acyclic graph, in which the nodes are tasks to be computed and the edges are data dependencies. And the good thing about scientific workflows is they already some of these scientific workflow systems that are available have a very good focus on integration of tool sets, so they already do that. And some of them are also there's also scientific workflow systems out there that scale and that use distributed infrastructure. But what these systems most of the time focus on is reproducibility. So the aspect of, can I repeat what I also said earlier? Can I repeat a scientific study? Because in science, it's always necessary that you can reproduce everything. And this was a major aspect for the scientific community all along. And then when you go and try to find a system that has all of that, it turns out that some of these workflow systems, especially the ones that scale, are limited to command line tools. And also what is to say there is, most of these, even if the scientific workflow systems scale, they were conceived at a time where all this big data technology wasn't established yet. And this is also something you can feel, yeah, when you use them. And what is perhaps the most important cornerstone here is that this representation as a DAG is a limiting representation. So oftentimes you have data analysis tasks that just don't fit in this model of representation. For example, if you have an iterative algorithm that consumes the output of the previous iteration, then it is something that you can't easily represent in a DAG. And what I think is a worthwhile approach is the combination of these two ideas, so functional programming and foreign language interfaces. If we have these two together, then this can bring us much further compared to the point where we are right now. And from functional programming, there's two things we can get. And the first is functional programming as a programming paradigm is very expressive. It's universal. Yeah? Most of the functional programming languages, can express any program. So this is something we want to have here in order to get rid of this limitation that DAGs can't express all the programs we might need. And also, what is very natural in functional programming languages is this data type of lists and operations on lists. And also, you have the possibility to use recursion to express iterative programs, even if you don't have any syntactic sugar on them. You can always use the recursion, right? So what functional programming gives us is a very general way to express data analysis. And the other thing we get from functional programming is that we have if we can assume that all subtasks, the subfunctions, are side effect free, and then we can parallelize the independent parts of a functional expression. And if we additionally don't execute each and every expression as soon as we get it, but try to collect as many expressions as we can before actually computing one. So lazy evaluation, then we can what we can get is automatic parallelism, and this is something, yeah, we want to use in data analysis.
Does the lazy evaluation play well with the tools like you're using? Basically, you're using like your smaller tools as sub-modules, and those are eager, they're not lazy. So how does this play together?
Yeah, so it turns out that it's not so much a problem that you have subparts of your program that are eagerly evaluated, as long as the overall computation. So in these tiny bits, yeah, you don't have control. So your foreign application, it might be lazily evaluated, or it might not be. But in any way, you cannot parallelize automatically in a piece of code you don't know, right? So this is not an opportunity anyway. So these foreign bits of code, they are always the granularity level at which you can do this, and you can't drill into these. But as up to these foreign code snippets, you can do that.
But, you might have problems with that granularity also, because even if it's an external call, it could be faster, very short, and the overhead of concurrent execution could be not paying off. So automatic parallelism is always suspicious, because you need more information to know if it makes sense.
Yeah, I don't know if I got the question right,
Yeah.
but if
How do you know if when it makes sense to parallelize?
I just always parallelize. I just
Always.
assume that all the tasks I have in my workflow are side effect free and cannot
But
get in the
not,
way of
not
parallelism.
not because of the defects, because concurrent execution has overhead.
Yes,
And
yes, and I incur overhead. That's true, but I assume that the chunks of work that I parallelize are big enough to not make a big impact if you also count the overhead. So I don't parallelize additions and multiplications. So that would be very stupid. But you can, if you have a job that runs for 1 minute or 1 hour, then it perfectly makes sense to take the effort that is necessary to parallelize it and run it concurrently.
okay, but you can use a library because the algorithm is complicated but fast. So in that case, it's going to be slower, because you don't need to parallelize very fast calls.
Exactly. You shouldn't do that. And it is up to the user to not use the system in a way that makes it actually slower. But yeah. Sorry.
There's a question.
So we don't have control over it. Yeah. So you have to use it in the right way.
So a little bit back to your problem statement, right? You mentioned this problem with different tools and the reproducibility problem, right? And this is not exclusive to academia. Industry deals with that problem as well. And we have solutions. We have containerization, reproducible builds, infrastructure as code. So did you look into this kind of approach, encoding this whole infrastructure, this whole workflows, and making it repeatable in this way? And
In the way industry does.
yes.
So if you refer to the way industry does it as containerization, so to use Docker or Chef or I don't know. Yeah. But the one thing is the infrastructure. So of course you need the right infrastructure to run this workflow on. But the other thing is, first, how do you organize distributed infrastructure? How does container X Y know when it has to start, when all the input data is ready for it? And the other thing, and which is the most important thing, is how do you want to express this kind of dependency graph? Yeah. So it's much more about how do I write down a program that distributes, that automatically parallelizes, that uses all these foreign applications, and not so much about the infrastructure. Then we can map this to any kind of infrastructure, and we mapped it to Hadoop, and we also it would be possible to do it on different infrastructures also. So the answer to your question would be uh, it's possible, and I think it's also a useful thing to use all the infrastructures that come from industry and are open sourced to execute these kind of data analysis applications. But what these infrastructures don't give you is a way to express the data analysis itself. It's just a way to execute it. Yeah. There was another.
Yeah, this is related to the other question. And let's pretend that I'm a street hustling consultant now, and I'm just saying, okay, you're doing it wrong. You should do microservices with Docker, like he said, and REST services, and you send all the data through REST. And what's your response to that?
Yeah, then do that. And if you're done first,
What
yeah,
then?
yeah. And if you're successful doing it with microservices and I don't know, then go for it. Yeah, I mean nobody stops you. I have my own approach. It's also, I mean, if you look at under the hood, yeah, when I come to present my language, it turns out it'll be in Erlang, and yeah, then you will have services and stuff like that. But that is not the point here. The question is how do you express your data analysis task, and not how do you implement all the organizational stuff right now on this high level. Yeah, and then when it comes to executing it, and when it comes to distributing stuff, then microservices and all this stuff will be a very, very nice thing to have. But yeah, not
It
much.
just doesn't seem very. I mean, sending all this data over REST seems very inefficient to me.
Yeah, exactly. Yeah, and that is also a point exactly. So you don't send the data over REST, you send it to a distributed file system, and you use data locality to alleviate that.
Okay, thanks.
Okay, and so these are these two things. Yeah, functional programming, cool stuff. You gain a very general way to express programs, and you can automatically derive parallelism. And the other thing is foreign function interfaces. So how would this look like in a functional programming language? Well, you just need to have a way to say for each function that you define, oh, okay, this will be in Bash, and then you call your command line tool. Or this will be in Python, and then you call your Python library. And this way of describing your foreign task or your foreign function, yeah, it gives you a very natural way to embed foreign code in an organization language. And the cost, essentially what you're doing, the activity of writing a function in a foreign function language is the activity of writing a wrapper. But we want to have this wrapper as low cost as possible. Yeah, should be a one-liner to wrap a foreign tool. And this is essentially what, thank you.
I wanted to ask, how are you leveraging the GPU power when you're writing things on those languages? How is the tooling? Because right now, when you're doing heavy computation, like crypto coins and all that stuff, it's supposed to be running on a GPU, but I don't know too much right now about the tooling that you're using. Um, is it running CUDA? Is it running like OpenCL, any of those, or it just runs on the CPU?
So no, not any of that. So it all depends on these foreign tools you include. So if these run on the GPU, then we run on the GPU, and if they don't, we don't.
How many of them run on the GPU?
I don't know any. Sorry.
Just a question, but is it a particular reason to have, looking at this, all these tags, I see a mix and match of algorithms, infrastructure, databases, and you have GPUs as well.
We do. Yeah.
With Phi. But at the end of the day, why do not characterize your workloads and say, okay, this is infrastructure, this is general algorithm. So what are you looking to achieve as a kind of um, system to perform orchestration between all these tools?
Exactly.
Or just to have a better way to handle your resources?
No, uh, it's a little bit of both, yeah. To have a system that lets you use all the tools, and also what I described earlier is we want to use parallelism, and this is exactly what you said, to to use the resources in the right way, but on a very high level. So it's not like, okay, here we have this machine and it has a GPU and perhaps it has ASICs inside, yeah, and we wanna get the leverage of this special purpose hardware. But if we say, okay, we have a cluster um, where every machine is homogeneous, yeah, and we know we can do this and that at the same time, then we want to be able to use these resources.
Okay, did you think about using Mesos and creating sort of a scheduler in Mesos to handle these type of things? Because you need to make a scheduling and orchestration of tasks. Then you get the result and then combine them. So you can write your own language to define what your scheduler should do and leverage metaschedulers, also Hadoop on beneath.
Yes. So yes, we thought about using Mesos. This is essentially this is a very good point, because Mesos is exactly it. It is a system that gives you scheduling and distribution right away, and we have an implementation on Hadoop, but it's not the only thing out there that manages your resources. Mesos is a very good example.
So I think one of the important distinctions between like Mesos and like what I hear you talking about is like Mesos just gives you resources. It doesn't actually like it'll run it and it doesn't give you any result from returning it. So like we're working on a similar thing where you run into this bottleneck of like I tell you I want this many cores and stuff, and it like is a nice tool for giving you that, but it doesn't actually like help you construct anything useful on top of that, or scheduling it, or stitching any kind of result back together. So I think that's an important distinction to draw if you aren't used to working with Mesos and just sort of like
Exactly.
know the word.
You're right, and this is why we just we're not done by just using Mesos. We have to put something on top of it in order to achieve exactly what Mesos cannot give us. So the piece of code that we are running on, like Mesos or any other resource management system, is has to do all that. It has to talk to a distributed file system. It has to give us return values, and we have to have a way to know of these values. And this is what we have to do here. Yeah, in order to do it that way. Okay. So this is my call. Oh my God. So what is Keyinform? It's essentially it's a minimal way of achieving just the two things I showed you earlier. So it is it gives you distributed execution. Right now we have an implementation on HT Condor and Hadoop. Mesos would be nice. It's driven by a functional programming language in which we assume that all the tasks are side effect free, they terminate, they're deterministic, and it gives you the possibility to draw in libraries from R, from Python, whatever. And then we can set out and take this scientific workflow where we have all these problems, yeah, and we can partition the data, infer the parallelism, and run it distributedly. So that is the core selling point here. And let's look at an example. So this is a task that does a very, that unzips a file. So we have this, the name of the task is gunzip. Don't get confused by the def task thing. It's just a definition of a function. And in scientific workflows, we're talking about tasks. So, It has one output, and it consumes one input, both are files. And now I say, okay, I want to write this function in bash. And then I step out and put in some bash code, and then I'm done. And then I can just call this thing like a function. And when I call this function on a list of stuff, then the language interpreter is able to find out that the unzipping of my archive1.gz has nothing to do with my archive2.gz, and then it can do this in parallel and distribute it on the cluster and whatever. Very simplistic, but this is essentially how it works. And then we can compose out of this all kinds of workflows. Right now on the website you can find examples. These are only from, there is a question.
I'm a bit confused because you say if you unzip a file, that's a side effect.
Yes, that's true. On the file system in the Unix thing, but what you get here is so at some point I have to introduce side effects, right? So there's all the tools, they access memory, they access a hard disk, but only for the workflow system it has to look as if there was no side effect. And when you look at the layout of this function, it consumes a string which represents a file, and it outputs a string that represents its file. And as long as this doesn't interfere with any of the other tasks, I'm cool. But of course, at some point, I have to allow something like a side effect. It's not like the Haskell way of things, yeah, where you try to keep everything side effect free until the bitter end. But these tools are they're not constrained in that very sense. So locally, they produce files and they consume files, and they maybe even talking to the internet. But eventually, it has to look like, yeah, as if they only produced something and didn't do anything to their environment.
It's just I kind of have the same problem. I don't really understand how. So you're saying that you're assuming that all of your tasks, like all of these building blocks, are side effect free and parallelizable. But that seems like such a big assumption. Like you're gonna have shared resources that they're gonna have to cooperate around. Like, how do you have a way to talk about that? Yeah,
that's true. This is the biggest assumption I have, and of course, if this assumption fails, then I'm done, and I don't have anything useful to offer. But it turns out, from experience, yeah, this is only because we look at the tools and look at how they work, and they work exactly like gunzip. Yeah, they consume a file, they produce a file or a set of files, and they most of the time they don't talk to the internet, and if they do, they don't change any state which could interfere with another state. So this is where I draw the validity of this argument from. Yeah, because all these tools do, it's okay to have this assumption, but it's not generally the case. That's true. I need to race to the end of my talk, I guess.
Actually, the audience is out of time, you guys.
So there's a lot of examples. They're all from bioinformatics. Check them out. This is how this can look like. So here we have a workflow and a description, and essentially this is commented code. So further down you find the code. And it has a beautiful REPL. And to wrap this up, what Cuneiform is, it's a functional programming plus foreign languages. It gives you distributed execution on multi-core HT Condor Hadoop, automatic parallelization. You have a very expressive way to express your data analysis workflows, and you can use all the libraries you already have. And I want to conclude this talk with a paper from '75. And there, Frank de Riemer said, by large programs, we may mean systems consisting of many small programs possibly written by different people. And if we take this literally, we also have to take into account that these programs are written in different languages. And yeah, usually I would ask for questions.
ask questions, but we should start changing rooms because there's another talk in 5 minutes in the other room. Both rooms, actually.